What's up, everybody? Welcome to Geology. Let's talk glacial features, and it's going to take a minute to get through, so pause when you need to. What I've got, I'll upload this. And I'm not saying you would necessarily fill in every box here, but I think some folks like to take some notes as they go. But maybe will just serve as kind of like the framework that we're going to need for all of these features. So yes, this is a lot of stuff, no doubt. But I'll also say here, hey, here's the big themes, and hey, here's some that are maybe not quite as common or quite as likely to show up on a test. So for the features, we'd want to think about, is this erosional or depositional? Is this a product of when the glaciers came through, them dropping something off, in which case it's a deposit, or them scraping something away, in which case it's erosional? So just think of that as I go through all of them. I'm not going to like fill this in as I go like I do sometimes. But what does it look like? That's what we're going to be doing for the bulk of this. Like, what does that feature look like? Where might you find one? Some of them are like everywhere. Some of them will have a specific spot, and then any like other random characteristics that might pop up. So print that if you want to. Ignore it if you want to. Your call. So what are the big themes? This is a picture of a glacial deposit. Oh, popped up on the own screen. Maybe we'll just make it big here. This is a picture of a glacial deposit from a SUNY Oswego field trip a ways back. It's the McIntyre Bluffs. If you've been over there from campus, you go over towards Sterling. This is an extension of the Sterling Nature Center, and you can drive right up to the edge and then walk out and check them out, down from the beach or up from the top. And what you may not notice if you're not a geologist, but what sticks out like a sore thumb is the nature of the deposit itself. Through your geology glasses, if you look at this, what you see are a mixture of particle sizes. It's unsorted, it's unorganized. And that's the very typical, usual textbook example of what we would expect with a glacial deposit. And again, once you're trained a little bit in this, you see it from 100 miles away. See how big that boulder is up there that's suspended in this spire? So we're seeing boulders. Remember the particle sizes? Boulders, cobbles, pebbles, sand, silt, clay. It's all here, and it's all just dumped in an unlayered mishmash. So why? The idea is that the glaciers are so big and so powerful that they bulldoze all of this, or they embed it in the ice as they flow. But when it's time for them to drop it off, boom, they just dump it. There's no natural system of organization to it. So an unsorted deposit is very typical of glaciers. Whereas sorted deposits, and this is a beach not too far away from that, and you can see, I know that these are formerly my dogs. They've passed on, but you can see that this is a beach made of all cobbles that are all about the same size. Going out to campus, right along from the health center over towards Rudy's and Bev's, and now the new brewery, you've got organized, sorted deposits. All those particles are about the same size. It doesn't look like this at all. It's not a mixture. So that's the big thing, right? Sorted versus unsorted. That theme is going to pop up a lot. So since we started with the bluffs here, and these are the same. If you go to McIntyre Bluffs, if you go over to Fairhaven Beach State Park, if you go to Chimney Bluff State Park, or if you get out in a boat somewhere down there towards Fairhaven and you turn around and look back at the shore, you just see bluff after bluff after bluff. That's a photo I should have in here. What they all are drumlins, but they're drumlins that have been cut by Lake Ontario. I can't really zoom in on this one right here, but this is about where, am I right on that? Where McIntyre Bluffs can be found. I mean, it's bluff. So there's like McIntyre, the state park. There's one called Sitz Bluff that I've ever really been to. But they're all this type of hill. They're all drumlins that have been chopped off by erosion from the lakeshore of Lake Ontario. Now, they're everywhere. So what is a drumlin? This shot right here, where did it go? Let me pause. I lost it. Sorry about that. We're back. That shot right there, that's the one I was looking for from a different slideshow, I borrowed this from the internet, but this is a very typical pattern of what you would see with a drumlin. This long, elongated hill, a steeper, blunter end on one side, and a more gradual end on the other side. New York State, and your textbook has a lot of these features, but it does a lot of them in Canada. So let's do a little bit more with New York ones. This is like a scanned image of the great upstate New York drumlin field. So basically, from Oswego to Rochester, north of the Thruway, is just packed with drumlins. This is Skinny Atlas Lake. North of there, up towards the lake, heading this way. Drumlin after drumlin after drumlin. I have Google Earth open too, and you can see it if you with the trained eye. You can see it a little bit. These longer hills that tend to be forested, they're not as easy to farm because it's a steep hill. And if you drive over this way, we have at least one classmate I know that makes this commute over from Oswego over towards Hannibal and then straight down into Weedsport. And if you take this route, you're going up and down hills the whole entire time. You're going along that longer axis of the drumlin. So like this is a steeper hill going right up there, and then more gradual coming down the back over here. And if you're in lab, we did topo map work with this drumlin right here. Steeper on one side, more gradual on the other side. They're everywhere. And if you drive east-west, you go up and down a lot more because you're cutting over like the short end of them. Which brings up the point that the steep end tends to point towards where the glacier came from, which in this case is the north. So if you drive up this side and then all the way back down, that'd be driving north-south. If you come across this way, that's going east-west. They are composed of glacial till, which is unsorted material. So again, the bluffs are truncated drumlins that have been cut in half by Lake Ontario. So they let us excited geologists go look at what the insides of these things look like. Hey, all right. How are we looking? Drumlin. Next. And again, the sheet doesn't quite go in this order, but I got them all in here at some point. U-shaped valleys. This is one I took of. This is outside of Tully. If you ever go to Labrador Ski Mountain or down towards Truxton, there's actually that little white spot right there. Hang glider fanatics take off from that spot right there because the steep valley coming down this side, it's just a good launch point. And then Labrador Mountain is right around this nub on the other side of that, down that side of it. It's not a mountain at all. It's the side of a U-shaped valley. So very typical to upstate New York, particularly once you get south of the Thruway down into the higher part of let's turn some roads off here. Into the higher elevation up onto the plateau, you'll get lots and lots and lots of U-shaped valleys. Finger Lakes, we'll talk about in a minute, are all U-shaped valleys. If you drive from Oswego south to Syracuse, it's reasonably flat for those two. And then when you get south to Syracuse, you're in the bottom of U-shaped valleys on Route 81 all the way down. You look to your left, you see a big steep flat hill. To your right, a big steep flat hill. That's a U-shaped valley from a glacier going in and coming back out. And remember, these things are like miles thick. They're enormous. So they carve that valley right out as they go. And this is a more dramatic version of one from somewhere out west, stolen from the internet. They're called U-shaped valleys because they've got this U shape, right? That's in opposition to V-shaped valleys, which would be carved by rivers. This V-shaped valley, carved by this river right here, is actually, if you go up this valley and then turn left, you can go hiking up in there. It's called Tinker Falls. Nice little waterfall, very short hike. That's the V-shaped valley caused by the river, and then you go out into this, and the U-shaped valley would be going perpendicular to that. In fact, you can see the other side of the U-shaped valley right over there. Glacial striations are scratches in bedrock from the weight of the overriding ice, particularly when there are cobbles, rocks of any type really, embedded in the bottom of that ice. And as that ice slowly scrapes over, it scratches the rock and leaves these behind. If you have the good luck to go to Central Park over Thanksgiving break, walk around, find some bedrock, and you will see scratches in it. And that is what this is from. That's striations from the glacier that was on top of that area, again, until about 10,000 years ago, going through all those ice ages. They're handy because they allow us to see what direction the glacier was flowing in. So that's a big thing. Scratches or grooves in bedrock that show the direction of glacial flow. Finger Lakes. which I probably should have just done with U-shaped valleys, but I didn't. There's an aerial shot of one. It's a beautiful area, long, narrow lakes, um, quite deep usually, that essentially fill in the bottoms of U-shaped valleys. Now, I know the reason I did it here because it's going to go into moraines too. This plateau here is tilted south, so it's like the water would like to flow on this map down, which is south, but the southern end of these are all blocked up by our next glacial feature, which is a moraine. So this one in particular is called the Valley Heads Moraine. It goes right through here, and that is turned into the drainage divide. So that's going to bring in some terminology from previous sections of the course. The drainage divide is that line that separates water that flows from one direction to the other direction um, into two separate watersheds. So the southern end of the Finger Lakes are essentially dammed in a sense by this giant moraine, and now they have backfilled those U-shaped valleys, and now the water exits all of these to the north up into the Seneca River, then over towards Syracuse. Yeah, if you want to know locally, well, I guess not locally, but if you're driving south for Thanksgiving, and you go down 81, you're going to get down into those valleys. When you get to the Tully exits, you'll see that the highway kind of comes up, and then you don't necessarily feel like you're deep in the valley anymore. Then you're on top of the Valley Heads Moraine. And in fact, when you turn around and come back to Oswego, when you go past that exit, that Tully exit, it's going to say, "Welcome to the Lake Ontario watershed, Lake Ontario drainage basin." Because north of that line, that water flows up that valley in through Syracuse, through Onondaga Lake, and up through Oswego. Whereas south of this, it goes all the way down into the Chesapeake Bay. Excellent. So I kind of threw a couple at you at once there, but so the Finger Lakes are the long, narrow lakes that fill up U-shaped valleys, right? Terminal moraine is what plugs it up. I guess I didn't really say what it is. This little diagram right here, although it's terribly out of focus, shows the glacier kind of acting like a bulldozer in a sense, that it plows forward, and as it does, scrapes up material with it. It will also have material embedded within the ice. So as it goes and it melts, the ice is gone because it melts, and it will drop off the sediment that it's carrying. And again, it's glacial till. It's going to be unsorted and build up this big pile. So again, the simplest way to think about it is a bulldozer. Shoves forward, drops the stuff, backs out, right? Maybe it's a tiny more intricate than that, but close enough. So this glacier came down from the south, made it that far, and then backed out. And again, through all of the ice ages, every 100,000 years or so, there was advances and retreats of these ice sheets, and we exist during one of the interglacial periods. Long Island is a kind of a grand example of a terminal moraine. So picture the glacier's moving forward, and on two separate advances, it left two moraines. What happened then in between them, if you can picture like a bulldozer goes forward, backs up, and leaves these two ridges. And after that, there'd be sediment washing off of them, which we're going to get to in a few minutes as well with outwash plains. But the bones of Long Island, and Long Island is there because of those advances of the glaciers, leaving those large two terminal moraines there. On that sheet too, there's lateral moraines. I'm probably less concerned about those. I mean, there's all kinds of moraines. Sorry, this slide looks weird. The terminal moraines are the ones that happen at the end. So like the valley heads, I can't pronounce the name of the Long Island one. Honestly, I got to ask somebody. Would be perpendicular to the way that the glacier flowed. So the glacier comes in and then backs out and drops it in that direction. Lateral or medial, and again, I won't get into being this specific, would be forming along the sides or in the middle of glacial flow as it goes like that. So let's just how about we just stick to terminal moraines, and we'll call that good. Composed of glacial till, a bulldozed long pile at the terminus or end of the glacial flow. Kettle Lake's an easy one. Big round lakes, fairly shallow, fairly small. They're all over Minnesota. Uh, what's the area? Near Song Mountain, there's a whole bunch. Which I should have put a bookmark it before. Not that far south. Not even that far south. There you go. So there's Song Mountain ski area and a bunch of kettles around it. You can see there's round ones, a couple connected. Small little ponds, essentially. And the idea would be that a very large chunk of ice, as this thing is retreating, a very large chunk of ice that didn't initially melt, got dropped, and as sediment is landing all over the place, being pushed around that ice block, once it eventually melts, the support for that is gone, it collapses, and you're left with that little lake. There's kettle holes, too. Like Iowa's filled with them. If they no longer are filled, spring fed or depending on the location of the water table, they can dry up and just be left with like a random kettle hole in the ground. Pretty easy one though, no big deal there. Outwash plains. So this would be a big one. So the map of Long Island again, you've got the moraines. Now throw 10,000 years of rain on top of those, plus all of the water, which was significant, that was melting off of the glacier as it retreated. And that's going to pick up a lot of sediments. So what's interesting here is that you get the moraine itself, which if we're following along should be unsorted materials, glacial till, and then the outwash plain south of that, which would be sorted materials, because now we've brought running water to the party. And that running water, as it slows up and speeds down, as we discussed in previous units in rivers, does a great job of organizing particles, because if it's going a certain speed, it can carry a certain size, and as it slows, it will drop those incrementally as it goes. Again, running water and wind sorts out materials naturally. So there's almost the whole story of Long Island. We could throw in some shoreline processes for the barrier islands on the very south edge of it, which we didn't really get into, but moraines with outwash plains interspersed between them. Esker and Kame. So if you're following on your sheets, these are probably the least likely to show up on a test. And I couldn't even really find a good picture, though. I can't find the map, but maybe I'll find it and try to put it on the test if I want to be clever that way, I guess. There are a couple of these show upstate New York, and I think according to this map that just barely misses my house by less than a mile, there is an esker nearby. So what it would be is a long winding ridge of usually sand-sized particles, a little bit more organized, again indicating that it's running water. So these could be deposited by like streams that are flowing down through the glacier as it melts. There's going to be water not just at the end, but like tubes flying through it like a crazy water slide, carrying material with it. And Kames, that's the esker. Kames could be a similar scenario. You get this kind of triangle-shaped hill from drainage coming down through a glacier. I wouldn't get. How about this? I won't put them on the test. They won't be an answer. The next three are alpine features so they happen in mountains. They happen from valley glaciers. This is one of my photos. This is climbing up Whiteface from the parking lot. I didn't do it from the ground yet, but towards the top of Whiteface Mountain, there's like the weather observation building at the top. You go right along this and you can park right back there. So you get to see all three of these here: Cirque, Arête, and Horn. Check those for the spelling there. French terms, I believe. So this is like this arrow is pointing to like the big bowl-shaped depression in the side of the mountain. So if you took a pre-existing mountain and took a big old, hypothetically, ice cream scoop, figuratively I should say, big ice cream scoop out of the mountain, that's what the glacier did. It scooped out some of that rock and carried it away, eroded it right away, giving us this big bowl-shaped depression. The arête would be that ridge on either side of the cirque. So if you got up on this, and you can see there's some other tourists climbing up the thing. There's a handrail there and everything. You're going right up the that ridge with a cirque on this side, a cirque on the other side. The arête is the ridge, and the horn is where all three meet towards the top. And we can look at it in Google Earth too if you want, but I'm not sure it would look much better than that. So it's right here. It is a ski area. There's the road that goes up it. So that bowl-shaped depression is the cirque. That image was from like over on this side. There's the arête, the ridge, with another cirque on this side, and the horn would be where all three meet. Now the vertical exaggeration is really cranked up here, so don't go thinking it looks just like that. Like that ski mountain looks a little terrifying with that vertical exaggeration up, but. And so that ski area is in a cirque itself. All right, what else we got? A couple more. Glacial erratic. If you drive around upstate New York a little bit, you're going to spot these things. If you see a giant rock that looks like it doesn't quite belong, it's most likely a glacial erratic. Yes, you can buy these from landscape companies, but it's relatively expensive, and there's enough of them just around. So look out at farm fields as you're driving around, and occasionally you're going to see just a big old random rock. The erratic part would indicate that it doesn't necessarily match the local bedrock, because again, glaciers are so big and strong they can pick up a rock the size of a house, carry it somewhere, and when they are done with it, they're done with it, and they drop it. So it doesn't necessarily match local bedrock. It's huge and random. It's a glacial erratic. Hanging valleys or hanging waterfalls. This is some professional photographer's image of Tacanic Falls north of Ithaca and Trumansburg. Beautiful state park. Recommended. The idea here is if you took a river, I wish there was one more photo here, one more like before photo. The glaciers carved this valley deeper. If we came before, this river may have been flowing across the image this way. Then bring in the glaciers. They're going to melt their way in and melt their way out and carve a deeper U-shaped valley with water in it, making it a Finger Lake. And now this river that was happily doing its thing and flowing right across, now all of a sudden rapidly drops down that side. And that's what the hanging part indicates, that it hangs over the other side. This valley hangs over this side. And then through the years, this and every other waterfall erode their way upstream as then dig their way right down in. And in fact, you can see this all over. We'll look at it in Google Earth. You might be able to see a couple here. You can barely make it out like that little tip right there. We'll find better ones. You can see this valley in just Skinny Atlas Lake right there. There's a valley and there's like a little delta that it formed outside of it. Let's go to Tacanic Falls. And these little deltas that project out into the lake are a result of all that erosion that took place. Then when the water flows out, it drops its sediment because it slows down. So this is Tacanic Falls, and that fall has like migrated its way all the way upstream. And you can, I mean, a beautiful place to hike. If our resolution will snap in here, you can also drive to some overlooks to see it. But if you can picture, maybe that's it right there. Google Earth doesn't really help me out here. But if you can picture, again, before the glaciers carved out this big U-shaped valley for the Finger Lake, that waterfall would have been just happily like up at this level, flowing and doing its thing. And now all of a sudden, it basically created the potential for that much energy for that waterfall to fall down the side, giving us that beautiful park and hanging waterfall. That's all it slides. Did I see one more on here? Glacial potholes basically dried up. Kind of like you did it. So big themes, sorted versus unsorted, get that down. Are they erosional or depositional? And is there anything that they specifically do, like tell directions, like drumlins can tell directions, striations can tell directions. U-shaped valleys can tell directions too. Don't worry about Esker and Kane so much, and I think we'll be in good shape. Thank you for sticking with this. I know that was probably a long one. How'd we do? 24 minutes. Good job, everybody. And good luck on the Glacier quiz.